S. Chand presents educational video lectures as per the new UGC CBCS curriculum. Absolutely free. Difficult science concepts made easy. Study anywhere, anytime.
Honey and water, both are liquids, right? But both are having different consistency. So have you ever given a thought that why does honey flow very slowly and water has a free flow? Welcome to S. Chand Academy. Myself, Dr. Mamta Sethi. So today we will be learning more about the properties of liquids. If you read more about this topic, you can refer to the book by S. Chand Publishing. The link to the e-book is given in the description box. In the previous lectures, we had understood about the properties of gases in detail. So we will be learning more about the liquid state in this particular lecture. So as to revise the concepts, we have already understood that gaseous state is the most disordered state of the matter, whereas solids on the other hand are most ordered state of matter. Liquids lie somewhere in between. We have many properties of the liquids, but to start with, to discuss more about this, we will be focusing mainly two properties, that is viscosity and surface tension about the liquids. So let us start learning about the properties of the liquids. So liquids have many properties. Unlike gases, liquids cannot be compressed, and unlike solids, liquids do not have a perfectly crystalline structures. Although the magnitude of intermolecular forces in liquid molecules is significantly higher compared to the gaseous molecules, right? So there are many properties of the liquid, but in today's lecture we will be focusing mainly upon two properties of the liquids. To start with, let us first understand the first property of the liquids, that is viscosity. So we know that liquids have a natural tendency to flow. So if a liquid falls on a surface, then it automatically starts flowing. But we do observe that some liquids, they flow very quickly, whereas the others, they take time to flow. It depends upon the various factors. Now, let us understand the reason why certain liquids have thick and have very high consistency, whereas the others are very of low consistency. So we all know that honey is mainly composed of fructose. So fructose, as we can see here, is having many such entities where it is able to form hydrogen bonds. So here lies the reason why certain liquids are thicker compared to the other liquids. Therefore, we can generalize it that the liquids which are more polar in nature and which have a tendency to form hydrogen bonds are generally thicker. It is this reason because of which honey is thicker compared to water, and we define here one more term, that is your viscosity. So what is viscosity? So there is an inner resistance from the molecules itself, the molecules of the liquids, towards the flow, right? The liquids will resist the flow of the of its own molecule, which is called viscosity. In other words, we can say that the resistance to the flow of the liquids is called viscosity. So depending upon the kind of intermolecular forces which liquid molecules can form, they can have high viscosity or they can have lower viscosity. Now, let us understand the factors upon which the viscosity depends upon, or the force with which a liquid flows depends upon. Now, to begin with, there are two kinds of flow. One is a streamlined flow. The kind of flow we will have of a liquid inside a tube, there are no disturbances. So this type of flow is called laminar flow, right? So this type of flow of a liquid is called laminar flow. But there is another type of flow which is not uniform, and rather, it has a lot of disturbances. The kind of flow we observe in a naturally flowing river. So this kind of flow is known as turbulent flow. So the calculations which we are going to understand today about the viscosity are for laminar kind of flow, that is the kind of flow which we observe in a closed tube. So let us understand that, let's say this is a tube in which a liquid is flowing. Now each of the layers, the liquid is flowing layer by layer. All these layers are moving with different velocities. So this layer, which is just next to the wall of this tube, will be flowing with a slow velocity. Now as we move towards the center, the centermost layer of the liquid is flowing with the highest velocity. Now this layer, which is next to the wall, is having highest amount of intermolecular forces, and the forces between these molecules and the walls of the container prevents it from flowing faster. Now as we move towards the center, these forces decreases, and therefore the liquid layer which is right at the center will be flowing very fast. Now the rate of flow of the liquid inside this tube is numerically related to, via this relationship, this is F is the force of flow. Now this force of flow is directly proportional to the area of contact. So area of contact between the two layers, so which is denoted by A. These layers are moving with velocity, like one is moving with velocity V1, another is with V2 and with V3 and so on. So there is a velocity gradient. So it is directly proportional to the velocity gradient, where V is the velocity, x is the distance. So this force of flow is directly proportional to the area of contact and to the velocity gradient. Now removing this proportionality constant, we can write that F is equals to minus eta A dV by dx. So you can see here that the two forces which are acting in opposite direction are, one is the force of flow and another, which is represented by the symbol eta, is the force of viscosity. So it is this term which is preventing the liquid from flowing very freely and quickly. So we also observe here that there is a negative sign. So why is there a negative sign? So this negative sign indicates that the force of flow with which the molecules are flowing in the forward direction and the viscosity which is resisting these molecules to flow in the forward direction, and hence it is acting in the backward direction. These two are in the opposite direction and therefore we have a negative sign. So eta is also known as coefficient of viscosity. It measures the viscosity of any liquid. Let us now understand that what will be the units of this viscosity, coefficient of viscosity. So we all know that in SI system, what are the units of force? Newton. Units of area? Meter square. Units of velocity will be meter per second, and the units of distance will be meters. Inserting all those units here, we will be having the units of eta, that is the coefficient of viscosity, equal to Newton per meter square second. So these are the units of coefficient of viscosity. We can also define these coefficients of viscosity, the units in CGS system. In CGS system, it will be dynes per centimeter square second. Since the the magnitude of coefficient of viscosity which we will be getting for many liquids is generally smaller in magnitude, therefore it is sometimes recommended to quote the values of coefficient of viscosity in CGS system. The alternative name for the CGS units of coefficient of viscosity is poise. So 1 poise is equal to 1 dyne per centimeter square second. We also can establish a relationship between the SI units and CGS units of the coefficient of viscosity. Now, there is another interesting phenomena that we observe in our day-to-day lives also, that whenever you must have seen in the kitchen also that if you start cooking, what do? First of all, you take a small quantity of the oil in a pan or maybe in a bowl, and then you start heating it. What do you observe there? You definitely observe that the oil, which was looking slightly thicker in the beginning, appears to be slightly thinner, right? This is precisely the effect of temperature on the viscosity of the liquid. So what happens? Let us understand now that what happens to these liquids when we increase the temperature. So the answer, of course, will again lie on the basis of, it can be explained on the basis of the intermolecular forces which exist between the liquid molecules. So we have already understood that compared to gases, liquids have higher magnitude of intermolecular forces or cohesive forces by which the liquid molecules are sticking to one another. Now what happens? Go back to the the lecture 1, that is kinetic theory of gases. So we have understood that as temperature increases, the molecules will start moving faster. Kinetic energy is a function of temperature. So as we increase the temperature, the liquid molecules will start moving with higher kinetic energies. Now higher kinetic energies, so they are moving so fast. So that's how they are able to break those intermolecular cohesive forces. So at an elevated temperature, the intermolecular forces gets weakened. So it is because of this reason the viscosity of a liquid decreases upon increasing temperature. The opposite trend, though we have already covered it in the gaseous state, but just to mention so that we can compare the behavior of liquids as well as gases. So this effect of temperature on viscosity is different. It is opposite in case of gases. In gases, what we observe that as we increase the temperature, viscosity also increases. Whereas in liquids, it has a inverse relationship, and the quantitative relationship between the temperature and the coefficient of viscosity is given by this particular equation, where eta is the coefficient of viscosity, E to the power EA, which is activation energy, R which is gas constant, and T. So since this temperature is there, but it is there in the denominator, so it has a inverse relationship with coefficient of viscosity. So eta is inversely proportional to temperature for liquids. Now we have understood about the term viscosity, and we have also understood that what is the effect of temperature on viscosity. Let us now understand that how can we measure the viscosity. So suppose I ask you that what is the value of coefficient of viscosity for water. Let us say what is the coefficient of viscosity for a liquid, which is, let us say, ether, which is if I ask you to calculate the coefficient of viscosity for an oil. So how do you measure that? So we have a very simple technique with which we can measure the coefficient of viscosity, that is eta, in the laboratory. And the apparatus which is used to measure the coefficient of viscosity is this is called Ostwald's viscometer. Since it measures the viscosities of a given liquid, it is called viscometer, and it was proposed by Ostwald, so it is called Ostwald's viscometer. Now before I start explaining you the working of this particular instrument, I would now like to discuss the theory behind this particular method. Now the theory comes from the Poiseuille equation. So this is a very famous equation, although there are a number of equations which explains the, which relates the viscosity of a liquid with other factors, but this is the most convenient equation which can be converted into the parameters which can be measured in the lab at ease, and we can calculate the coefficient of viscosity. Now according to the Poiseuille equation, this is the volume of a liquid. What volume? We are talking about the volume, a fixed volume of the liquid that we are going to take in the viscometer is related to the parameters, the physical parameter, that is, it is related to the pressure. P here is pressure, T here is the time of flow of the liquid. Now eta is the coefficient of viscosity. We have already learned this nomenclature. Now what is this R and L? What we see here, that inside this particular viscometer there is a capillary. What is this? This is a capillary. Now what is the purpose of this capillary? This capillary is there to have a controlled flow of the liquid. Now R and L are the radius and the length of this capillary. Now again go back to the same equation. According to this equation, eta depends upon these factors. Like the coefficient of viscosity depends upon the pressure, it depends upon the time of flow, it depends upon the radius of the capillary, and it depends upon the length of the capillary and how much volume of a liquid we have taken in the viscometer. Now what do? Suppose we want to compare the coefficient of viscosity for two liquids. So what do? We are trying to, we will use this particular apparatus, and in this apparatus, what do? We will take a fixed volume of the liquid. Now if I take two liquids over here, liquid 1 and liquid 2, I will take the same quantity or same volume of the liquid. Now if I use, and also the capillary has a, it has a definite size, radius and length of the capillary, they are already fixed. So out of many factors, radius, radius of the capillary, length of the capillary and volume, they are fixed. So pi by 8 is also a fixed number. So what does coefficient of viscosity depends upon? Eta then depends upon putting a constant for all of these, like pi by 8 r raised to power 4, L and V. We can write here K, which is constant. Eta is related to the pressure and time of flow with a constant over here. Now this constant represents the parameters which are there for the capillary. Now let us use this equation. Suppose I have two liquids, liquid 1 and liquid 2, of which the coefficient of viscosity are eta 1 and eta 2, and we can write simply here that eta 1, we take the ratio of the coefficient of viscosity for the two liquids. I will be able to write K P1 T1, since for the two liquids time of flow is going to be different. Okay. K and K gets cancelled, right. So we have eta 1 upon eta 2, which is equal to P1 T1 upon P2 T2. Now again this pressure depends upon what? Pressure is related to density via this relationship. So pressure is related to height, to the density of the liquid, to the acceleration due to gravity. Now if we are going, so we are going to clamp this particular instrument at the same height. So height will remain same, and this value of G at a fixed height will also be same. Therefore the pressure will depend upon what? It is only a factor of, it is only dependent upon rho, that is density of the liquid. So we can see here that the relationship that is obtained after inserting the relationship between pressure and the density of the liquid, we get eta 1 upon eta 2 equal to rho 1 T1 upon rho 2 T2. So we can have a quantitative expression which relates the coefficient of viscosity for two liquids, which is directly. So coefficient of viscosity is directly proportional to the density of the liquid and is also directly proportional to the time of the flow. So higher the density of the liquid, higher will be its viscosity and more time the liquid will take to flow. So knowing this expression, if we know the coefficient of viscosity of one liquid, then we can find out the coefficient of viscosity for the other liquid. Now very quickly I will explain you the procedure that how do we measure this coefficient of viscosity using Ostwald viscometer. We take a fixed volume, this is kind of inverted U-tube where there are two bulbs. This bulb has two marks, upper mark and lower mark, into which we place a fixed quantity, let us say 10 ml of the liquid. Now we are going to clamp this particular instrument, viscometer, using a clamp from this side. So and we will allow this liquid to fall from this upper mark to the lower mark, and let us say we will count that how much time a liquid takes from this mark to this mark. So we will have time of flow, we will take exactly equal volume of the other liquid and again calculate the time of flow from this mark to this mark. So in this way we will have T1 and T2. Densities of the two liquids can be measured by taking equal masses of the two liquids and then by using the relationship between weight, volume and mass of the two liquids. So this was all about viscosity of the liquid. Now to start with another property of the liquid, I would like to ask a question to all of you, that you all must have observed dew drops on the the surface of the leaves, or you must have seen the drop wise flow of a liquid. So have you ever thought about the fact that why are these drops spherical in nature, or why do they immediately try to form a kind of drop on the smooth surface? Let us take a short break here and we will answer this question after the short break.
Hello everyone, I am Dr. Seema Thakran. Welcome to S. Chand Academy. I will be teaching you topics limit and continuity, differentiability, partial differentiation, tangents and normals, curvature, curve tracing and many more. Please like, share and subscribe S. Chand Academy, and don't forget to press the bell icon for the future updates.
Welcome back to S. Chand Academy. So to answer the question that I asked you before the break, let us understand another property of the liquid which is very important, and that is your surface tension. Now let us go by the literal meaning of the surface tension. So the tension which exists at the surface, very simple meaning. To explain it further, let us understand this concept by having a look at the molecules at the surface, right? This is the surface of the liquid. Suppose we have taken, a liquid sample. Now we see that these liquid molecules, there are molecules in the bulk and there are molecules at the surface, right? So the molecule which is present in the bulk is experiencing forces from the different directions, and these forces are somehow balanced, and therefore the molecule which is present in the center or in the bulk is experiencing no net force, whereas the molecule which is at the surface is experiencing kind of unbalanced forces, the forces which are pulling it in the downward direction. There are no upward forces. So this molecule or all other molecules which are present at the surface, they have unbalanced forces. So they are always in the state of tension. So what happens that these molecules which are in the state of tension can be assumed to have higher energy. We know that something which is unstable, which is will be having higher energy. Now and this obviously will like to acquire a state in which the energy of the system is lesser. So what will happen that in order to acquire the stable state, or in order to acquire the state which is having less energy, these molecules will try to come back, or they will try to roll down towards the bulk. So what will happen that the surface of these molecules is always stretched towards the bulk. So this tension, this force which exists at the surface of the liquid, and what will be the direction of this force? This force will always be in the right angle. It is at the right angle to the surface. So this is known as surface tension. So we can always define the quantity surface tension of a liquid. It is the force acting per unit length along the surface of the liquid at an angle which is right angle to the any line which is taken on the surface of the liquid. Now surface tension is a very important property of the liquid. Because of this surface tension, the droplets of water will try to acquire the spherical shapes. Now why spherical only? You see on the drops which are there on this leaf, they are what? They are spherical in shape. So it is the natural tendency, because of surface tension, the natural tendency of the liquid to acquire minimum possible surface area, and out of all the geometrical shapes which are available to us, sphere has a minimum surface area, and it is therefore the droplets are, the drops of water or any other liquid, they are spherical in shape. Now that means, because of this surface tension, the liquid molecule will try to shrink. Now what are the units of this surface tension? The surface tension is represented by the symbol gamma, and the units are very simple since we defined it as force per unit length. So force has unit Newton in SI system and distance is expressed in meters. So the units of gamma in SI system are Newton per meter. Let us now understand that what is the effect of temperature upon the surface tension. We know that surface tension is there, like tension exists at the surface, liquid molecules will try to acquire minimum possible area, but what will happen if you increase the temperature? Will the tension at the surface remain same or will it be different? So we know that as temperature increases, the surface tension of the liquid decreases. So it is again because of the decrease in the magnitude of the forces, intermolecular forces, which gets weakened upon increasing the temperature. So what happens? That at an elevated temperature, the molecules are moving with higher kinetic energies. Higher kinetic energy, and therefore they are able to, these molecules are there but they are moving with faster velocities, higher kinetic energy. They move so fast that they are able to cross that barrier, or the barrier which is deciding or the intermolecular forces, the magnitude of these cohesive forces which binds the liquid molecules together. So at higher temperature, these forces gets weakened and therefore this tension at the surface decreases. Now there are other phenomena also by which the surface tension of a liquid can be decreased. Very briefly, I would like to mention that you can also reduce the surface tension of a liquid by adding soaps and detergent to the water, and this particular phenomena is very useful in washing the clothes, right? Cleansing action of soap can be, you can refer to the book for more details, but just to mention here that soaps and detergents also lowers the surface tension of the liquid, and in fact, when the temperature reaches the critical temperature, the surface tension completely disappears. Now why completely disappears? Because at critical temperature, liquids start converting into gas. Liquid converts into gas completely and there is no surface of separation. So if there is no surface of separation, there is no question of surface tension. So let us now understand that how can we measure this surface tension in laboratory. A very simple instrument which is known as Stelligmometer can be used to measure the surface tension. This instrument is also known as dropping pipette. Now we can understand that why do we call it dropping pipette? Because it looks like a pipette except the point that it has a capillary inside. Now capillary again is to control the flow of the liquid so that the liquid does not fall freely and it comes out drop wise. Now when the liquid falls from this dropping pipette or stelligmometer, just when it is about to fall, the drop of the liquid is about to fall, there are two forces which are acting. One is the force due to weight because of which the liquid drop will fall, and another is the force of surface tension, because of which the liquid molecules are stretched or being pulled in the upward direction. Now when the drop has not fallen and is only sticking to the tip of this stelligmometer, the two forces balance exactly each other, and this equation forms the basis for the experimental measurement of the surface tension. Now according to this equation, the force due to weight, which is equal to mass into acceleration due to gravity, and the force of surface tension, we know that gamma is force per unit length. So if this is force per unit length, if we multiply this with the length, which in case of a circle or sphere is equal to 2 pi r, this will become force, and therefore equating the two, we get a quantitative relationship between the surface tension of a liquid and the mass of the drop. Now there are two methods. The first one we call it drop weight method, and the other one we call it drop number. Now in the drop weight method, what is done? Now this has a capillary which is fixed, therefore apart from 2 pi r is also fixed. So what does gamma depends upon? Suppose I take two liquids, then W1, the ratio of their weights, which is equal to M1 G upon M2 G. G will remain same at a fixed height, and it can be written as 2 pi r gamma 1 upon 2 pi r gamma 2. So we know that G remains same, and here also 2 pi r can be cancelled because we are allowing the liquid to fall through the same capillary, and therefore gamma 1 upon gamma 2 can be calculated by taking the mass or the weight of the two drops. So what we do, that we take a fixed number of drops. We take, let's say, 10 ml of water or 10 ml of other liquid, and then what do? We take the weight of the drops that we have calculated. Suppose we take 20 drops, right? We count 20 drops in a weighing bottle and we take the weight of those 20 drops. In the next go, we change the liquid, any other liquid, we again take 20 drops and then note down their weight. And by finding out the ratio of their weights, we can actually find out the surface tension of one liquid. The surface tension of water is generally known at different temperatures, therefore water is chosen as a reference. If we know the surface tension of water, of any other liquid can be easily compared. And in the second method, which is again derived from this expression only, that instead of finding out the weight of a fixed number of drops, what do? We count the number of drops. So here what we do, we just replace the term mass by, volume of one drop into density. So this is what? Weight of a drop only, but weight of a single drop. But we know that it will be very difficult to calculate the weight of a single drop. So therefore what we do, we prefer to calculate the number of drops forming out of a definite volume of a liquid. So again we would be calculating the number of drops which are coming out of, say, 10 ml of water, and then in the next go we change the liquid, we take another liquid and we allow that liquid to fall, and we count the number of drops forming from a different liquid, and calculating their ratios we can calculate the surface tension of any given liquid. So in today's lecture, we have mainly discussed the two major properties of the liquids. One is viscosity and another is surface tension. Their temperature dependence, and also we have discussed the experimental measurement of viscosity and surface tension in the lab. To read more about this topic, you can refer to the book by S. Chand Publishing, the link to which is given in the description box. Please like, subscribe and share, and do not forget to press the bell icon. Thank you.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.